We will be talking specifically about the diagnostics of logistic regression. In this video, we will show how to use Cook's distance to find influential points in the data. We will also show how to use AIC in model selection, and we will also show how to use R output and convert log odds into probabilities. We will be using Cook's distance to identify influential points in our dataset. Cook's distance is very important in finding influential points that may change the interpretation of the data drastically. Influential points can be characterized as extreme individual data points which can alter the quality of the logistic regression model. We can graph Cook's distance of each point, and this can show which points are the most influential and which ones we need to keep an eye out for. In this video, we'll be using the R packages Tidyverse and Broom. Here we are showing Cook's distance per observation. It was coded to show the top 3 most influential points regarding Cook's distance. So if we were to go look at index number 11, 44, and 87, we would see that those are the most influential, quote-unquote, out of the ordinary points. To go even further than using Cook's distance, we can standardize the residuals and see which ones fall outside of the range of -3 to 3 standard deviations shown on the next slide. To do this in R, it is coded as follows. Here is shown the standardized residuals plotted for each individual point and by species. So we can see that none of the residuals fall outside of the -3 to 3 range. So this means that our model fits soundly. Now we will be moving on to the model selection using AIC. For logistic regression, we can use AIC to assess which model is best in predicting our categorical variable of interest. AIC estimates the quality of each model, with the lowest AIC being the best model. To do this, we can use the mass package in R using the step AIC function in order to pick the best logistic regression model. The output uses a forward procedure, adding the most significant predictor one by one. That is, adding the predictor which lowers the AIC the most. Species is our binary response with 0 or 1, with 0 equaling versicolor, 1 equaling virginica, and predictor variables sepal length, sepal width, petal length, and petal width. For our first video on the AIC interpretation, we are using the stepwise AIC function. So when you use the R code that is as follows right here, this is the first set of output that you will get. There are multiple sections of the output, but this will be the first section. So what we're seeing here is the species with each variable listed. So for example, species and petal width would yield an AIC of 94.48. And then species with petal length would yield an AIC of 99.059, and so forth. So, like I said in the slide before, you want to add one variable at a time. So since petal width has the lowest AIC associated with species, that is what we are going to add. So as I said before, there will be multiple sections in the R output when you use the function given on the last slide. So since we added petal width last time, we are now building upon that. So species with petal width is the new baseline equation and the associated AICs that you would get by adding each of the following variables. So for example, species and petal width and sepal width would yield an AIC of 90.132. And then again, species, petal width, and petal length would yield an AIC of 94.358, and so on. And they even give you the option of adding no variables, which would not decrease the AIC, so that means we still want to add more variables. And like I said before, sepal width now has the lowest AIC, so we want to move forward, add sepal width to our new equation, and continue on. So we're moving on to the fitted model with just a simple one variable case. So the general logistic regression formula is with probability that yi equals 1 given xi equals x is as follows right here. And we will use the call right here in R, and this will yield an intercept of negative 7.279 with petal width having a slope of 4.432. So if we wanted to put this into context of our problem with the probability that the species equals 1, which in our problem is the Virginica flower, given xi equals x, we would have the following equation right here. And this just turns our output from the log odds into probability, which is given from our output, but this is the equation to turn what you have given in the R output into a probability. So just for fun, we wanted to find the 50-50 point using our data set. So what this means is we wanted to find the point where the odds of the plant being, versicolor or virginica would be 50-50, or percentage would be 50-50. So since the odds are equal to p over 1 minus p, this would mean that the log odds be equal to log 1, which would be equal to 0. So that would yield 0 equal to beta naught plus beta 1 times petal width. So doing some simple algebra, we would get the equation negative beta naught over beta 1. And with the data we have, we would get negative 7.279 over 4.432, negative, because the negative times negative is a positive, and it would yield 1.642 centimeters. So if a flower with a petal width of 1.642 centimeters, or if we found a flower with that petal width, there would be a 50% chance that it would be versicolor and 50% chance it would be virginica.